welcome. Thank you again. Let's give another round of applause for the organizers. This is really hard to do. It's incredibly hard to organize these kinds of conferences, and I remember firsthand, so I have a lot of gratitude for everybody who played a role in making this happen. I actually came to PyData London in 2017, I think, so a long, long time ago. So I'm back now. And what I would like to talk about is mistakes. And actually, one mistake that I made is when I was writing up kind of my idea for this talk, I was thinking back and thinking it had been about 10 years. And so my talk title in the program is Data Science 10 Years In. But it's actually been about 15 years. So mistake number one. Let's talk about mistakes. I think that the idea for this talk actually came out of a conversation about mistakes with my teenager. I have a 13-year-old. And it was around this sort of conversation about this new kind of language that is developing with young people. And they've sort of invented all of these new words. It makes me think about how language is alive. And we are spending all of this time now building large language models that are always going to be stale by definition, right? Because they're trained on corpora that are from the past. And people are always changing language, right? So language is alive, it's evolving. And so a lot of the most charming mistakes, I think, that these language models make is that they're stale and they don't understand what young people are talking about. And so I was trying to convince my son that ChatGPT actually does not know everything. And he was like, prove it. And I was like, all right. And so I said, ChatGPT, what is a skibbity toilet? Which is something that he and his friends now say to each other. And it did not know the answer. In fact, it told me that I should ask my son for the answer. And so then I wanted to give him another example. And so I said, one of the things that I have been noticing is that social media is one of the things that is changing how people talk. The algorithm, which is now people talk about it as though it's this sort of anthropomorphized thing that exists. The algorithm is sort of tracking what we say, and all of these social media applications have mostly heuristic filters, I think, for some of these terms. And so because of that, language has evolved. And so one of the things that I've been noticing on people's social media feeds is that people have navigated away from using words like kill or suicide or dead because they believe, probably rightly so, that there are some kind of heuristic filters on the applications that will result in you being shadow banned if you use any of these red flag words. So people started using the word unalive recently. And I first started noticing it, probably many of you started noticing it on social media, but people now say this word in real life. Which I think is fascinating. And so I asked ChatGPT, why do people do this? And ChatGPT is wrong about this, right? So ChatGPT says that this is being used euphemistically or humorously. But actually, I think that it is a subversive language change. It's us injecting more perplexity intentionally as humans. As a way to navigate around constraints of the applications that we use, which I think is really interesting. This sort of has, led me to sort of think about, well, what does it mean then to make a mistake? What do we mean when we say make a mistake in the context of, applied data science, applied machine learning? And so I kind of was looking at some of the kind of recent examples of this that probably many of you have also noticed. So Twitter's bot didn't understand that the phrase throwing bricks was a euphemism. And so it incorrectly suggested that a basketball player was vandalizing things when actually throwing bricks just means, it's a basketball kind of euphemism. And famously, very recently, we were instructed to put glue in our pizza to make it more chewy, gluey. And also, we've been, I think, starting to talk as a community about, mistakes around copyright infringement and data privacy, and maybe even, who owns your voice, who owns the pictures of you, who owns the things that you write. But, in a totally different way of thinking, these are all problems that all of you have made happen in your projects too. These are mistakes that we all make as data scientists all the time. Classification errors, super common, right? Who has not made a classification error before? Overtraining, right? So when the model memorizes that one Reddit post from some other 13-year-old, not my son, who said to put glue in your pizza, right? If you memorize the data, then that's sort of what happens sometimes. And probably many of you have experienced problems around data provenance and data quality and dubious data sourcing. So I think that one of the things that's happening is that we are kind of out there pointing fingers at some of these applications of generative AI and kind of applied AI in social media applications and in industry, instead of looking inward at the mistakes that we are all making and what we are contributing. And I think that we need to maybe reconsider that. Because I think that dunking on these solutions is a little bit in bad faith. And maybe we could get away with it for the first 10 years of data science. But I don't think that we can anymore because people are starting to notice that we don't know everything. We have an extraordinarily low success rate in data science for successful deployments as a community. And this is, I think, becoming an existential threat, right? Because if we are associated with people who fundamentally cannot deploy and cannot deliver, then there is no reason for us to be doing what we're doing, right? So I think it's good timing for us to be kind of thinking about what we are not doing correctly and being a little bit more honest with ourselves and with each other about the mistakes that we're making. I love this quote. It's one that I think about a lot. The first 10 years of data science, a lot of mistakes have been made. And one of my concerns is that if we don't talk about them, that we are going to end up carrying them into the next 10 years. And we will just sort of keep making the same mistakes. So, deep breath. Let's get a little bit vulnerable and talk about some of the mistakes that we've made. I think that, part of the issue with talking about these mistakes is that in data science, mistakes sort of fall into one of two categories. Either mistakes that are embarrassing or mistakes that are expensive. So, for example, embarrassing mistakes, research code. This is embarrassing. Trying to deploy Jupyter notebooks. But vendor lock maybe is an example of something that's not embarrassing, but is very expensive. And I suspect that many people in this room are suffering from vendor lock issues Here's another one, right? So training all these models is consuming energy, right? It's consuming non-renewable energy. It's using up water, and it's using up time. And probably everything else sort of fits at the intersection of both embarrassing and costly. And this sort of has disincentivized, I think, us from talking about the mistakes that we're making. So, all right, let's talk about one mistake that I think that we all made as a community. And in fact, this image is one that I believe I showed, not exactly this image, but a version of this image is something that I showed in the talk that I gave at PyData London in 2017. And I said, this is the machine learning workflow that we use in industry to do applied classification. You have sort of training instances, you featureize them, and then you have labels, and you use that to produce, to train a model, and then you can, serialize that model, and then as new data kind of flows in, you vectorize it according to the original vectorizer, and then you can kind of generate prediction. But, as my 13-year-old would say, you're doing too much, right? This is, in reality, this is not how applied machine learning ever works, right? This is sort of kind of putting way too much pressure on, a single model, kind of this artifice, this idea that, one single model can solve, applied problems. That's ridiculous, right? The reality is that, I think what we've learned over the last 10 years and what is starting to sort of emerge, in actually many of the talks that you will see at the conference this weekend, that the reality of applied machine learning is that in order to actually do kind of, industrial grade machine learning applications, you need a lot more than a single model to rule them all. All right. All right, let's get even a little bit more vulnerable here. So, as John mentioned, one of the projects that I spent a lot of my early career on was the Yellowbrick project. It's a Python library. It's still actually one of the most, it's in the, I think, top 10% most downloaded packages on the Python package index. My co-creator, Dr. Bengfort, is here. So he and I created this library. It was really mostly for our students. We were teaching machine learning to students and trying to figure out how to help them understand, when they were going off track, when their model wasn't as predictive, or why it wasn't as predictive, and maybe if they should, select a different model, or if there was some kind of other featureization or pre-processing that might need to happen in order to produce a more predictive model that wasn't overly complex. So in the kind of pursuit of building Yellowbrick, I spent a lot of time looking at a lot of different visualizations of the machine learning workflow. And one that I personally got really stuck on was stochastic neighbor embedding visualizations. So if you've never kind of explored these, it's a way to compress, extremely high dimensional data like text data, which is what I've worked with for most of my career, compressing extremely high dimensional language data into 2 dimensions to try to look for patterns. And I think that I went down a lot of rabbit holes trying to look for signal in these sort of very simplified 2-dimensional plots. And then at some point at a PyData event, I spoke to a researcher, Leland McInnes, which some of you may know. And he was like, oh yeah, TSNE is sort of famous for visual hallucinations and the crowding problem, which is, when you compress things into 2 dimensions, you end up with things that are basically on top of each other. So it's really hard to see the nuance of the patterns. And so he actually was doing research on a different type of embedding technique called UMAP, which has turned out, I think, to be superior in a lot of ways. But that was after I'd spent hours, weeks, months, trying to look for a signal in these visualizations to figure out how to, build these into kind of standardized machine learning workflows. I think another mistake that I made very early on in my career was this sort of idea that active learning was the best way to produce labeled data in the case when you did not have labeled data. And so if you've never done active learning or heard of it, it was this idea that data scientists could annotate their own data. I don't think this is actually a very good idea, because if you are not a domain expert, you probably should not be applying labels to the data, because the way that domain experts kind of think about data is very different from how kind of people who are generalists or maybe kind of coming in a consultative capacity understand that data. But I spent, an embarrassingly long amount of time working with the active learning component of the dedupe library, which actually dedupe is an excellent library. Forrest Gregg created this library around the same time that we created Yellowbrick. And it's, it's an entity resolution and reconciliation tool, but it has a component that is for active learning, where you would look at examples from the data. It would serve them to you through the CLI, and you would say, are these 2 things the same? Are they different? Or I don't know. And I spent hours and hours and hours trying to produce labeled data, and it never really helped with the problems that I was trying to solve. Another one is synthetic oversampling. I know that from an academic and research perspective, this is a totally legitimate technique, but I will tell you that I have never, ever seen it work in an applied context. So if any of you has had a different experience, please come and talk to me. But this one, I think, ended up being another rabbit hole for me. So I think one pattern here is that there are a lot of rabbit holes in data science, right? You can kind of get stuck exploring the data for a little too long. And it ends up being essentially like dragging your feet. It slows down kind of moving towards a solution. Okay, let's get a little bit more vulnerable. So when I finished my PhD program, data science was actually just starting to exist. There was no such thing as data science when I was in school. But what there was a lot of PhD students who did not have jobs, and I was one of those. And so I ended up going into government work right out of my PhD program, and I went to Washington, D.C. So in Washington, D.C., I worked for a United States agency called the Occupational Safety and Health Administration, which is empowered with protecting the health and safety of American workers and ensuring that employers at workplaces are doing things to make sure that their employees don't get sick or killed. And so I had this sort of exciting, sort of promising job all of a sudden, and I felt like I was going to go and help save lives. It was really very exciting, and right away, it did seem like there were some really interesting applications of data science. And the first one that I found was the idea of inspection targeting. So we're looking at the state of Texas here. I'm actually from North Carolina, but for weird reasons that are a little too complicated, North Carolina is exempt from occupational safety and health administration at the federal level. We have a lot of strange rules. The states have a lot of power in the United States. But Texas is under the jurisdiction of federal OSHA, and it's where my dad grew up. And he grew up in El Paso here, so that little circle there at the tip of the kind of yellow part. It's where my father grew up. So in Texas, there are a bunch of different OSHA headquarter offices. And so this is where the inspectors who are trained, they understand things like manufacturing and healthcare and construction. Those are the three kind of most dangerous and deadly jobs. So they deeply understand, they've been trained, so they work in these different offices. And what they do is if a fatality occurs, then they drive to the location of the fatality, and it's based on their jurisdiction. So if you're in El Paso, and you're in the El Paso office, and a fatality occurs on the other side of your jurisdiction, you have to drive out there, and it's a long way to travel to do that inspection. It's about 500 kilometers to get to make that trip, and that's one way. And then once you get to the facility, you have to do the inspection, which takes hours, right? Because you have to go through and kind of do an analysis and understand what happened, that kind of caused this fatality or severe injury to occur. And so, I'm kind of coming in green out of my graduate program, no experience in industry at all, except I worked at a sandwich shop when I was in college to help pay for school. But there was a lot of enthusiasm in this time period, right? We sort of felt like it was a new world, and all of a sudden, there was a lot of ideas about bringing things like data science into the government to try to help and solve problems. And so, what I was thinking is, the business goal here is to figure out how to use a very small budget and do targeted inspections so that you don't have to necessarily traverse, a huge amount of distance in order to preempt dangerous scenarios. So what I was thinking is, okay, well, we have like 40 years of data of all of the facilities where serious injuries and fatalities have occurred. And we have a lot of information about what happened, right? Because these inspections collect a huge amount of data. And a lot of it is text data, but it's also a lot of structured data. And so I thought, well, let's look through the last 40 years of data and identify kind of the patterns, and then we can apply those patterns to companies that have not been inspected for the last 3 years. And in this way, I thought, I will fix the government with this data science stuff. And I felt very confident. And so I actually did train a model. And I actually was able to, at least with the training data that I had, predict some of the places where fatalities and serious injuries did end up occurring. The problem is that when I sat down, I sat down with the leadership at the Occupational Safety and Health Administration, all of these people who had been doing this for a long, long time through many, many, many administrations. And they patiently listened to me present this, my model, my results. And then one of them stood up from their chair and walked over to a bookshelf and took a book down, which is this book here, 29 Federal Register. And they opened it up to a page, it's probably page like 5 or 6. I didn't get that far. It's page 5 or 6. And on that page, it says essentially that there are 3 scenarios in which inspectors are allowed to do workplace inspections. Either somebody can die, and then they're allowed to go. A worker could complain, right? So if somebody calls and says, I believe that I'm at risk for falling off of a roof because they're not giving me the proper harness when I get up there and do roofing or in healthcare, having lifts off the bed so that people aren't physically lifting patients because it's extraordinarily dangerous for your body to lift bodies all day long. So worker complaints or random selection. Machine learning is not random. So my model was not a good fit, and they essentially told me that it would take so many lawyers in order to use this model that I probably would be retired by the time they were able to implement it. And that was a blow. And so I didn't retire right away, but I did go to another agency a few years later. I went to the US Department of Commerce. And still like the long Obama administration. So it's still a lot of funding going towards applying data science to fixing the government. And the goal now, I'm at the US Department of Commerce. I'm working with the International Trade Administration. And the goal is to figure out how to foster economic growth for American exporters. And so similarly to my mental model of how to fix the government in OSHA, I thought, I'm going to look at features of companies that are successfully exporting goods to other companies or to other countries. And then I will find US companies that match those features who are not already exporting. And in this way, I will fix the government with data science. And so this time, I actually had buy-in from the agency, so that's one less mistake made. And so I kind of started by using kind of all the traditional techniques that you learn in school, right? Use lasso to try to figure out which features are important. And then trained a model to do binary classification. I picked a random forest model initially, and then after talking with some people who are a little bit smarter than me, I realized this is a really dumb idea because linear models and nonlinear models make decisions in completely separate ways. And so you don't want to do feature selection with a linear model and then use a nonlinear model. So that was an embarrassing mistake, but I recovered and I trained a better model. And I actually, this time, was able to successfully find a large number of companies who appeared to be poised to be really excellent exporters. And I sort of had computed that this could actually have a statistically significant impact on the American economy. So I was very, very excited. So I sat down with the experts at the International Trade Administration, and I gave them my PowerPoint presentation and presented my model and my results. And they all looked around at each other, and then they looked at me and they said, this NAICS code, so North American Industrial Classification System, 488510, corresponds to freight transportation arrangement. And they said, you cannot export logistics because logistics is exporting. So that was embarrassing. But eventually, we did figure out a few things, a few industries that we could help. Later, things shifted in politics, and I went to the private sector. And I was working at a company, I'm not going to, at least not on stage here, talk about this, but you're welcome to chat me up later at the social hour. And the goal here was to try to figure out how to connect, to do entity resolution across different social media platforms for sales enablement. And it was essentially just like one mistake, one catastrophe after another. And here are three of the ones that stand out the most in my mind, which is they hired me because they wanted me to help build an inferencing API on top of a few models that they'd already built, right? So we wanted to be able to deploy it in a Kafka kind of microservices architecture. So, Kafka would have like a new event come through, and the event is like some information about a social media profile. And the idea was to kind of, wake the model up, the kind of serialized model up, do a prediction, and then do kind of, metadata labeling and entity reconciliation on the fly. But the models were all built in Spider notebooks. And so I had to essentially rewrite everything, and it took me months, and they were furious because, from their perspective, the models were already trained. They were ready to go. That was really hard. Another thing that I discovered in doing that project is that some of the models had been trained on extremely questionable data, which I will not say any more about here, but again, you're welcome to chat me up later. And so what we had to do is we had to pivot and create a new data ingestion system. And I will tell you, if you want to build a data ingestion system with just data scientists, good luck, because we are not trained in a lot of our kind of education and boot camp programs. We do not get training in how to do kind of high throughput data ingestion. And so I was learning Go and implementing this system at the same time, and it was Thanksgiving, and my boss was yelling at me all the time because it was late. So this was extraordinarily stressful. So a few years later, different job, more mistakes. So now I'm at a, let's say, customer service organization, and the goal is to figure out how to route L1, L2 help desk things in a more automated fashion. Probably something that's close to what a lot of people are working on now, figuring out how to do kind of more kind of routing within applications in an automated fashion. The idea was to kind of train a model on historic CSR records, so like a complaint came in or a help desk request comes in, and it ends up going to L1, which is a human. And then that smart human says, okay, well, you need to go talk to this person. And so there's a record of those routing decisions. So we can, in theory, this is a multi-class classification problem, right? Okay, so the problem is that what the company said they wanted was AI. And at the time, that still meant like deep learning. Now I think it just means code. But at the time, I took this at face value. They want deep learning. I got you. So we started off with a model that was way too complicated, and it was a TensorFlow architecture. It had way too many layers, way too many parameters. Training took an extraordinarily long time. The tuning was very difficult because we were working with a huge multi-dimensional space of hyperparameters, and we also didn't do a great job of capturing our experiments. And I think that this is a very common mistake in data science, where you're just sort of like doing a lot of random experimentation and not documenting, this model came from this specific data, it was trained in this way, it took this long, the model is this big, serialized on disk. Those are all actually very important things you need to know when deploying a model in production, and we were not recording those kinds of things at the time. So we tried again, and actually we ended up picking a simpler model, right? And it was much better, but it still really underwhelmed the leadership because the overall F1 score was not anything that exciting, although on a per class basis. Was actually doing very well, which now in retrospect, I would see this as like a win, right? Because even if you can predict some of the classes, you're kind of cutting down the amount of human in the loop like by a lot, right? So it doesn't, the overall F1 score like almost is kind of irrelevant, right? Because if you can kind of with a high degree of confidence even kind of cut some of the work down. That translates to a lot of dollars saved. But I didn't know how to make that argument then. Instead, I presented them visualizations. And I said, look at the per class classification, and they did not understand what I was saying. So I tried again. And on this third attempt, we got a model that was good enough. But then we made the mistake of going straight from research to deployment. And what that meant was that we were deploying Jupyter Notebooks as code. And there was no packaging, there was no versioning, there was no linting, there were no tests, and most importantly, there was no plan for drift. And this is before MLOps had been invented, so we didn't even know that that was going to be a problem. And then, in March 2020, all of the data that started coming in was suddenly very different. They were calling the help desk and saying, I can't connect my computer to my printer. And that did not appear in the historical training data at all. And suddenly it's because everybody is working from home. And all of the incoming data is completely different from the training data. And I love this expression, production is noise. And I can't remember who said this. If anybody knows, please come up and tell me, because I think that this is like the perfect kind of punctuation here. So just to kind of sum up here, I think of myself now, I think more as an engineer than I do as a data scientist. And I think it's because I've sort of learned all of these hard lessons that data science really only gets you so far. And then you really need to be an engineer to make things work. And in engineering, we call these kinds of things anti-patterns. And it's a really convenient term, right? Because the word anti-pattern gives us a vocabulary for talking about mistakes in a way that allows us to sort of talk about them not in the first person. Mistakes were made. That's an anti-pattern. I think that we need to talk more about anti-patterns in data science. And so here are, some of my top anti-patterns for the first 10 years. Potentially some of these are ones that you also recognize and have also seen. This is not a comprehensive list, but that sort of self-indulgent experimentation, hours and hours looking at t-SNE plots and doing active learning, kind of having no understanding that my downstream users could not even use machine learning at all in order, to meet regulatory requirements, having like a complete disregard for data provenance. Lots of these things are probably things you recognize, and I think estrangement from engineering culture, might be the most serious one, because I think that the first 10 years of data science was really a time where data scientists kind of held this, position of power in their organization because it seemed like they had this magic ability, and because of that, they haven't really been held accountable for just doing kind of basic engineering things like sprint planning or PEP 8, I think maybe we need to kind of shift away from that and start to really recognize these as anti-patterns. I suggest also that, when you talk about these mistakes, that you practice using the first person. Maybe I made a mistake when, or we made a mistake, because the reality is that your mistakes are what make you. The reason I am an engineer now is because I learned the hard way, that you need to be very careful about, submitting API keys to GitHub, right? So we learn these things the hard way. We learn how to build ingestion systems because we show up for work and realize there's actually no data at all for us to science, right? So, the mistakes make us, and that, I think, should empower you to be willing to be a little bit more honest with yourselves and with each other about these mistakes and anti-patterns. So just to kind of leave you with this last thought, an expert, and I know there's been a lot of discussion about experts in the AI sense, but this is also true of humans, right? An expert is a person who has made all the mistakes that can be made in a very narrow field. And once you start to feel like you have made enough mistakes in a narrow field, it might be time to branch out a little bit. So thank you so much. I hope you enjoy the rest of this conference. This is my LinkedIn. If anybody wants to connect with me, I'd love to. And please come and chat me up later, and let's talk about mistakes together. Thank you.